My name is Grace, and this is Josh, and we are graduate students at the University of Tennessee in Knoxville. Thank you for coming today to listen to us talk a little bit about using Mathematica for higher level thinking in calculus. Last semester, we were able to teach calculus with Mathematica using a design by Dr. Brodsky at the University of Tennessee. This semester, we had the opportunity to create our own version of Calculus 3 with Mathematica. So today, I'm going to talk a little bit about the bigger picture and the structure that our class fits in, which is the inverted classroom. Josh is then going to talk a little bit about the goals in designing this class and how Mathematica plays a role. And then I'll wrap up with some of our plans for next semester. So our class fits into the big idea of an inverted classroom. An inverted classroom takes the introduction material and pushes it to before class so that students are first exposed to the material on their own and they can develop a basic understanding of it. And then in class, we focus on working on problems either together or individually. A nice way to think of this or visualize it is with Bloom's taxonomy. So Bloom's taxonomy gives a nice picture of the process of learning. For an inverted classroom, students are first kind of build that basic foundational knowledge and a little bit of comprehension outside of class, which is thought to be easier to do. And then in class, we solidify the comprehension and move forward to possibly applications and analysis. So we work together in class to kind of do a higher level learning. How this works in our world is that before class, students read notes and watch some videos to get that knowledge base. And then they do practice problems over that basic introductory material that allows them to build some kind of comprehension of what's going on. In class, we spend a day doing an activity which either focuses on application or analysis of the material, so some kind of higher level concept. And then we also have a day dedicated to problem solving, so where students can work together or individually and ask us questions and see what's going on. So this is the big idea of the structure of our course that it fits into. And I'm going to turn this off for a second so we can pass it over to Josh, and he can talk a little bit more about how Mathematica comes into play with this.
Okay, so now I want to talk a little bit about our primary goals for course design. So how did we want to design this course, and what were we trying to accomplish? So we had a few different goals in mind. So our first one was to make sure we had really clear student expectations. What were we expecting of our students? What were they going to do? We really wanted to make that crystal clear from day one and continue to remind them throughout the semester. And our second goal is really to make really nice, manageable notes. And that's kind of vague, so I want to talk about what I mean by that. Okay, so there's really two primary ideas. So one is we want these notes to be manageable for our students. So this means they shouldn't be too long or too complex, right? Remember, this is where our learning starts. Our students haven't seen the material yet when they're reading these notes, so they need to be very basic and easy to digest. Another is we wanted to make sure that it was a complete core of material. So what I mean by this is that it covers the basics and it doesn't branch out too much, but the notes stand alone. So later sections in the notes don't rely on extra things we've covered earlier, only the notes themselves. Okay, so it's standalone. And a third goal, which kind of goes along with the first and second, is we really wanted this to be easier for new instructors to pick up the notes and to use them and to adapt them to their own classes, so they could create their own auxiliary materials to go with the notes. Third, as this is kind of the primary point of the talk, is we wanted to engage our students in higher thinking during the class. This is just a general goal. And kind of going along with the third goal, we wanted to focus on conceptual understanding instead of computation. We're doing multivariate calculus, and as many of you may be aware, if you don't do this, there's an awful lot of computation that you can have to wade through in Calculus 3. So how did we want to focus on conceptual understanding? First, we really wanted to steep it in a geometric viewpoint. It's multivariate calculus, so there's lots and lots of pictures. We wanted to make sure students could see these and maybe even create their own pictures on their own so they can have that viewpoint that everything is geometric. And we wanted to focus on some main ideas. One was linearization, limits, additivity, and then lastly, just coordinates and different ways of viewing the different geometries when you're describing shapes. All right, so now I want to talk about how we're going to accomplish these goals and what Mathematica has to do with that. So how do we use Mathematica to accomplish all those goals? So just a little bit to say about the notes. Again, it's a core material. Pretty much we just define what our concepts are and we try to give an intuitive explanation. There's not a lot of proof, theorem and proof in the notes. This is because I feel that theorems are harder for the students to understand at this point, so it's mostly intuitive explanations of why things work the way they do. And there's lots and lots of examples in the notes. We actually want to add even more. And these are often presented through Mathematica so that we don't really cover much of the computation in the background. We just give them an idea of how do you approach this problem conceptually, and this is the code that goes through those steps. And the Mathematica is in the notes. They can easily work with it on their own. Okay. So here's a nice little sample from the notes. So what have we got here? So here they're parameterizing an ellipsoid. And you can see I'm mostly doing this in tech and explaining, but then I have a nice little quip down here where I have a bunch of Mathematica code that not only computes the ellipse and the tangent plane, but also gives us a nice picture. So that's something that's very common in our notes, just have pictures of all the different things that are going on. And of course, the code, so that they can produce it on their own later. Okay. All right, so let's do this way. Okay. So after our students have looked at notes, they do something called pre-class practice. The idea behind this is it's fine and good to read through notes, but you need some time as a student to work with the ideas on your own before you're asked to do something more complicated. And so this is just a little notebook file with some introductory questions and problems and a little bit of guidance to help the students get started on everything. And we present our commands in bold, and we try to introduce them to the Mathematica commands as we go. Our students have no background in Mathematica when they enter this class, so it's really, really important for us that we guide them step by step so they get used to using the programming. Okay, so finally, this is the in-class part. After we have done notes and practice, they come to class and they do an activity. So these activities are probably the most elaborate part of our course design. And students show up to class in a computer lab and they work together in small groups, usually 3 or 4 students in a group. And they do a bunch of stuff in a notebook file. So the notebook file typically has a little introduction and then some stuff for them to work through. And these are very important. These involve Mathematica because we ask them to do a lot of computation in just one class period, and it's not really doable without Mathematica. So here's a nice example where we have them look at limits along different paths. You can plot it and see that it's not continuous at the origin, and then they can prove it by looking at several paths. So you can see they get several answers. Here's a different one where we're looking at more of an application of vector fields. We had them look at electric fields, plot some of them. And we also had them look at divergence and curl and discovering some of how the math they've learned relates to physics and different applications. And the last little example, this one is probably my favorite here. this is really asking them to dig deep in a concept that's, I think, is very challenging for our students, which is the second derivative test. Our students are not required to have linear algebra before they take Calc 3, and most of them don't know very much linear algebra. So dealing with the second derivative test and finding eigenvalues for a Hessian matrix doesn't mean much to them. They don't know what an eigenvalue is. And so this activity, we tried to let them visualize that. So they looked at the linearization of the gradient, which uses the Hessian, and they can see that the eigenvalues mean something in this vector field. Right? They have to do with directions of going in and out. So being able to visualize that allows them to understand something that normally they don't have the tools to do, which is really cool. And so the last part of what we're doing after they've done activities and we've kind of built them up, made them ready, we have them work on homework on their own. And then finally, at the end of a unit, they take an exam. And then all of their homework and all of their exams is done in Mathematica. And they're allowed to use any command they like. And this makes computation pretty simple because they've got a lot of power here with Mathematica. And so to kind of make sure that there's a check on here, they're not just coding things that they don't understand. Actually, most of the grade is from explaining their answers. So they have to explain in text and words what's going on, how does their solution work, and why does it work. And here's a nice little quip from an exam of a student's solution. So we asked them to find a distance between a circle and a line, and you can see they have a little list of how they're doing it, and then why that method works. You can see the code is actually a very small part of their answer here, not too much. Okay, and they have a little bottom line.
Okay, so this is our first semester implementing these notes and these tools. But based on mid-semester feedback, we already have some changes we want to put in place for even our next unit and next semester. Looking to the beginning of next semester, we want to create a smoother start to the course. Our students have never seen or used Mathematica before, for the most part, so throwing Calculus 3 and Mathematica at them all in that first couple weeks can be a little bit overwhelming. So we want to try to figure out how to kind of ease them in to using Mathematica. It's nice at the beginning they can check their work by hand because we're doing vector calculus at the beginning, so it's something that's easy to compute and double check yourself by hand. But eventually, once we get further into the material, Mathematica is going to be the main thing. If you checked yourself by hand, it would take a very, very long time. So in an effort to create a smoother start, we want to add more Mathematica-based explanations to the first couple units. And also to transition the pre-class to be more of a guided practice so that we can introduce them maybe more fluidly to commands, syntax, that kind of thing. So that's something I'm actually hoping to put into place starting next week to create kind of this guided practice feel instead of a list of problems and a to-do list. Also, something we're looking forward to tackling for next semester is to create some videos to go along with our notes. Right now we have all the kind of written material, a handle on that, but creating videos so that we can appeal to more varieties of learning and kind of give them options. If they didn't understand something when they read it, maybe watching it will help, or kind of playing around with it that way. So that's what we're looking forward to do next semester and next week. So thank you for listening. Do you guys have any questions?